Test. All right. Okay. I don't know. Something happens sometimes. Okay. So. All right. I think I'm going to jump to chapter 10 because we're not doing alkynes and alkenes in my class. I kind of wish that he just followed the order of the textbook. So then I like. Because the problem is now when I'm reading the textbook, they're going to refer back to old stuff, but I don't care. Okay, so we're going to read chapter 10 and chapter 11. And we're going to do a bunch of problems. And the problems are going to be the important part. But first, I just want to understand how to name alkyl halides. Preparing alkyl halides from alkanes. Radical halogenation. Okay. Oh, yeah, this allylic thing is important. Preparing alkyl halides from alkenes. Allylic bromination. Allylic is when the carbocation is resonance stabilized, I believe. And I always read carbocation as carbocation. Anyone else do it? It's when the carbocation is resonance stabilized. Allylic means the carbocation right, yeah. I mean, it's really all about the pi. It's all about the pi, bro. Vinylic, I've never heard this. Yeah, it's probably because it's an alkyne thing. All right. Alkyl halides are encountered less frequently than their oxygen-containing relatives and are not often involved in the biochemical pathways of terrestrial organisms. But some of the kinds of reactions they undergo, nucleophilic substitutions and eliminations, are encountered frequently. Thus, alkyl halide chemistry is a relatively simple model for many mechanistically similar but structurally more complex reactions found in biomolecules. We'll begin this chapter with a look at how to name and prepare alkyl halides. We'll see several other reactions. Then in the next chapter, we'll make a detailed study of the substitution and elimination reactions of alkyl halides, two of the most important and well-studied reaction types in OCHEM. Now that we've covered the chemistry of hydrocarbons, it's time to start looking at more complex substances that contain elements in addition to C and H. We'll begin by discussing the chemistry of organohalides, compounds that contain one or more halogen atoms. Halogen-substituted organic compounds are widespread in nature, and more than 5,000 organohalides have been found in algae and various other marine organisms. Chloromethane, for instance, is released in large amounts by ocean kelp, as well as by forest fires and volcanoes. Halogen-containing compounds also have an array of industrial applications, including their use as solvents, inhaled anesthetics in medicine, refrigerants, and pesticides. All right, so we got trichloroethene, halothane, tetrafluoropropene, tetrafluoropropene, what? Okay, whatever. And bromomethane. Still other halo-substituted compounds are used as medicines and food additives. The non-nutritive sweetener sucralose, named Splenda, contains 3 chlorine atoms, for instance. Sucralose is about 600 times as sweet as sucrose. So only 1 milligram is equivalent to an entire teaspoon of table sugar. A large variety of organohalides are known. The halogen might be bonded to an alkenyl group. Alkenyl group. That's probably how you say it. Alkenyl group. A vanillic group, or an aromatic ring, or an alkyl group. In this chapter, however, we'll primarily be focused with alkyl halides, compounds with on a saturated sp3 hybridized carbon atom. Names and structures of alkyl halides. Let me get my notes. Okay, names and structures of alkyl halides. Although commonly called alkyl halides, halogen-substituted alkanes are named systematically as haloalkanes. Treating the halogen as a substituent on a parent alkane chain, there are 3 steps. Find the longest chain, name it as the parent. If a triple bond or double bond is present, the parent chain must contain it. Oh, really? Wait, that's weird. Okay, I'm gonna skip that. I don't know anything about that. That's weird. Name the number the carbons of the parent chain beginning at the end near the first substituent, whether alkyl or halo. Assign each substituent a number according to its position on the chain. If different halogens are present, number each one and list them in alphabetical order when writing the name. If a parent chain can be numbered properly numbered from either end by step 2, begin at the end near the substituent that has alphabetical precedence. Yeah. In addition to their systematic names, many simple alkyl halides are also named by identifying the first alkyl group and then the halogen. For example, CH3I can either be called iodomethane or methyl iodide. Such names are well entrenched in the chemical literature and in daily usage, but they won't be used in this book, thank God. Iodomethane. So what is this called? This is actually called... What is this actually called then? How else could you call it? I feel like that one is okay, right? Okay. 2-chloropropane. Bromocyclohexane. All right. All that stuff makes sense. Halogens increase in size going down the periodic table, so the lengths of the corresponding carbon-halogen bonds increase accordingly. In addition, CX bond... CX bond strengths decrease going down the periodic table. As we've been doing thus far, we'll continue using an X to represent any of the halogens, a Ficklebrine. Okay. All right, so the bond length goes up 40, 20, 20. And this goes down by a factor of 2. So this, okay, well, whatever. In our discussion of bond polarity and functional groups, we noted that halogens are more electronegative than carbon. The CX bond is therefore polar, with the carbon atom bearing a slight positive charge and the halogen a slight negative charge. This polarity results in a dipole moment for all of the halomethanes, and implies that the alkyl halide CX carbon atom should behave as an electrophile in polar reactions. We'll soon see that this is indeed the case. Dude, I love these diagrams. Honestly, I wish, like... Okay, give IUPAC names for... Okay, so this is just going to be... It's either going to be iodobutane or one iodobutane. It's probably one iodobutane. so let's just do this. 1-iodo-butane. This is going to be, you want to keep the lowest number first. So this is going to be 1-chloro-4-methyl-butane. 1-chloro-4-methyl-butane. Okay, this is going to be, I'm pretty sure you want to go from this side because you want to keep the numbers as low as possible. So this is going to be 1-bromo, 2,2-dimethyl, 1, 2, 3, 4, 5. So it's going to be 1-bromo. Oh, wait. I think it's actually going to be 1,5-dibromo, 2,2-dimeth, butane or pentane. 1, 2, 3, 4, 5. Pentane. Okay, here, 1,3-dichloro, 1,3-dichloro, 1, 2, 3, 3-methyl butane. Okay, E. This is a fun one because they're probably trying to trick you what the longest chain is. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, this is a tricky one. I think then 1, 2, 3, 4, 5. Oh, 6. Okay, they made it easy. If this was one longer, it would be kind of weird. But so all you're going to do is 1-chloro, 1, 2, 3, 4. 4-iodo. Wait, did I count that right? Oh, it is a tie. Okay, well, in any case, this is definitely the longest chain. So it's going to be 1-chloro, 4-iodo. Oh, wait. It's going to be 1-chloro, 4-I. Or no. 1-chloro, 3-ethyl, 4-iodo, pentane. One, 2, 3, 4, 5, 6. Bromo takes precedence. They're just trying to test you on the rules. This is going to be 2-bromo, 5-chloro. 2-brom, 5-chloro. What is it? Hexane? Yeah. Okay. Draw the structures. Yeah, actually, I want to have some fun today. This thing's going to run out of battery, I think. Okay, well, while it lasts, let's just do this. Oh, you gotta be kidding me. I think that, yeah, that doesn't fucking work. I don't know why that doesn't work, but it doesn't work. Okay, I probably gotta log into it here again. I actually like that they just email me because it's like, Can I get a theme change? It's like Frozen. All right, we're ready. I'm making a new one because this one already had stuff in it. Oh, actually, wait, I have an idea too. I didn't know I could do this until yeah, go back. I didn't know I could really do this, but I'm gonna copy this. I'm gonna go here. I'm gonna go to this new one and paste this thing in. Paste it in. Okay. All right. All right. So 2-chloro, 3,3-dimethyl. Okay. 2, 3, 4, 5, 6. Cl. Okay, that's it. 3,3-dichloro, 2-methylhexane. 2, 3, 4, 5, 6. The thing here is that it's because of the alphabet. So I probably got the alphabets thing a little bit wrong. No, wait. Three bromo, 3 ethyl pentane. 2, 3, 4, 5. 3 bromo. Sometimes, what's weird is that in the textbook, they always write right to left for the chains. So they'd have all these flipped around. I don't know why they do that. All right. 3 bromo, 3 ethyl pentane. So actually, I'm going to do it like this. Make it a little more tetrahedral. And this is going to be something like that. Okay, 1,1-dibromo, 4-isopropyl cyclohexane. Okay, so let's just start off with this. Okay, so we got the cyclohexane. Now let's just call this 1. So this is brom. Okay, now just call it going clockwise. 1, 2, 3, 4. This is going to be like that. Something like that. Okay, I'm going to zoom out a little bit. Hopefully that's still viewable. Okay, E. 4-sec-butyl. Ooh. Okay, yeah, I'm not the best with the T's and the S's and all of that. All right, chlorononane. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Actually, you can count the bars. 1, 2, 3, 4 plus 1. It's 9. Okay. So 2-chloro. All right, I'm gonna do it their way. Let's count. Let's go right to left because I know that that's gonna be the answer, and I'm gonna be confused. All right, so that's 2-chloro. Now we got sec-butyl. So the sec-butyl, I'm pretty sure that means like that. Because it's a secondary carbon. If not, we're going to have to review that one. I don't know if that's right. All right, another cyclohexane. Oh, here we got the tert. Okay, so 1,1-dibromo. And then 4 tert. So I think what that is it goes like this. Because we have, C1, C2, C3, C4, and it's tert. It's a third degree one. So I think that that's what that's about. All right, so it's time to check answers. So we're going down to chapter 10. Oh wait, I never switched it over. I knew it, bro. I always mess this stuff up. It's okay. You guys didn't. Here's the answers. Wait. Here's what I wrote down. All right, I'm not gonna go through them, but that's just an L. Okay, so chapter 10. All right, so wait, I got 1 iodobutane. That's correct. I got 1 chloro. I counted wrong. I said 3 methyl but 4. I said 4 methyl butane. Yeah, it's 3. Okay, but that's like minor. All right. 1 5 dibromo 2 methylpentane. Okay, that's what I got. 1 3 dichloro 3 methyl butane. Okay, that's good. 1 chloro 3 ethyl 4 iodopentane. Oops. 2 bromo 5 chlorohexane. Okay, that's good. Now let's look at these drawings. Yeah, see they draw right to left. I don't know why they do that. Okay, these look right. This one. Yeah, that looks right. That looks right. Oh, that looks right. E. Does E look right? Chloro. Yeah, E looks right. That's good. That's the one I was kind of confused about. Okay, good. And the tert butyl is also right. All right, no problem. Okay, so now we're going to get into section 10.2. Preparing alkyl halides from alkanes, radical halogenation. So this is something that's probably not really in my class, but I just kind of want to read it. As we saw briefly in section 6.6, simple alkyl halides can sometimes be prepared by the radical reaction. So radical meaning something that has an odd number of electrons. That's my understanding. Of an alkane with a Cl2 or Br2 in the presence of UV light. The detailed mechanism is shown in 10.2. Okay, so yeah, so here, this is a photon, and it splits the relatively weak bond. Propagation steps. Oh, this is so cool. I actually love this. And apparently like 200 million gallons of this stuff is made or something like that. I don't remember what it was exactly, but per year. Here's a step 1. So here, H3C, it doesn't have a formal charge, but it is a radical. So you split the bond, you form 2 chlorine radicals. The radicals react with the methane to form a, it's not a carbocation, but it's a carbon radical or something. Oh yeah, so here we get ethane. Here we get chloromethane, and here we get chlorine gas again. The overall reaction is the reaction of methane with chlorine gas to form chloromethane and hydrochloric acid. The repeating cycle part is really interesting, though. Because it's like the chlorine breaks apart, and then once the chlorine breaks apart, it takes a hydrogen from methane, but it takes it what's it called homolytically. It takes it where it splits it. Okay. Radical substitution reactions require three kinds of steps: initiation, propagation, and termination. Once an initiation step has started the process by producing radicals, the reaction continues in a self-sustaining cycle. The cycle requires two repeating propagation steps in which a radical, the halogen, and the alkane yield. The cycle in which a radical, the halogen, and the alkane yield alkyl halide product plus two more radicals to carry on the chain. The chain is occasionally terminated by the combination of two radicals. Unfortunately, alkane halogenation is a poor synthetic method for preparing alkyl halides because mixtures of products invariably result. For example, the chlorination of methane does not stop cleanly at monochlorinated stage, but continues to give a mixture of dichloro and trichloro and even tetrachloro products. Interesting. The situation is even worse for chlorinations of alkanes that have more than one kind of hydrogen. Chlorination of butane, for instance, gives two monochlorinated products in the 30-70 ratio in addition to multiply chlorinated products like dichlorobutane, trichlorobutane, and so on. Another example, 2-methylpropane isn't this just called isobutane? I'm pretty sure this is called 2-methylpropane. Yeah, okay. Just gotta check. As another example, 2-methylpropane yields 2-chloro, 2-methylpropane, and 1-chloro, 2-methylpropane in a 35-65 ratio, along with more highly chlorinated products. Yeah, so of the monochlorinated products, this is the ratio. That's what they're saying. From these and similar reactions, it's possible to calculate a reactivity order toward chlorination for different kinds of hydrogen atoms in a molecule. Take the butane chlorination, for instance. So this one is actually not at the end. That's interesting. Wait, butane has 6 equivalent primary hydrogens? Oh, yeah. Oh, yeah. And secondary hydrogens. Right, I forgot about this. Okay, yeah, you call a primary hydrogen something that's attached to a primary carbon. The fact that butane yields 30% of 1-chlorobutane product means that each one of the 6 primary halogens is responsible for 30%, 5% of the product. Similarly, the fact that 70% means that 17.5%. Thus, a secondary hydrogen reacts 3.5 times as often as a primary hydrogen. A similar calculation for the chlorination of 2-methylpropane indicates that each of the 9 primary hydrogens accounts for 7.2% of the product, while a single tertiary hydrogen reacts for 35% of the product. Thus, the tertiary hydrogen is 5 times as reactive as a primary hydrogen. Interesting. The observed reactivity order of alkane hydrogens toward radical chlorination can be explained by looking at the bond dissociation energies. Wait, what does that mean? The observed reactivity order of alkane hydrogens toward radical chlorination. Okay, so you got to break down these words. There's a lot of words in here. the reactivity order, I believe that just means the sorting of, the reactivity order of alkane hydrogens. What it's saying is exactly what it means. Okay. Toward radical chlorination can be explained by looking at the bond dissociation energies. The data show that a tertiary CH bond is weaker than a secondary, which is in turn weaker than a primary CH bond. It's weaker. Since less energy is needed to break a tertiary CH bond than to break a primary or secondary CH bond, the resultant tertiary radical is so that would be the C without the H, I guess, is more stable than a primary or secondary radical. Yeah, I mean, this is really important. I mean, and I'm pretty sure this pattern extends not to just carbon radicals, but also carbocations, where there's no radical electron. All right, okay, this problem, okay, I think I saw this problem. Draw and name all monochloro products you would expect to obtain from radical chlorination of 2-methylpentane. 2, 3, 4, 5. Okay. Oh wait, we have our thing. Trying to up the production value a little bit. We'll see. This might slow me down too much. I don't know. Okay, so let's just draw the molecule. So this is equal to, C. I don't know how much of this I want to draw. It's such a pain in the butt. 1, 2, 3, 4, 5. Okay, then we have a C here. Okay, so I think what they want us to do is kind of so this is a 3. This is, so okay, we have 1, 2, 3. We have 3. So that means 9 primary hydrogens. For 2, we have 1, 2. We have 2. So that means that we're going to have 4, 2 times 2 primary hydrogens. We have 4, or secondary, sec H. Okay, now 3, we have 1. So that means that we have, 1 times 1, 1 hydrogen. So what they're trying to say is draw and name all monochloro products you would expect to obtain from the chlorination. I mean, I don't know what that means really. Does that mean like you could do 1 chloro, 2 met pent. That's the first one. You could do 2 chloro. Now, this is interesting. Actually, if you put the chlorine on here, this is the same thing. So it doesn't matter. Because you would just change what the primary chain is. So that you can actually skip. Then you could do 3. You could do 4. And then 5. 5. You could do 5. I'm not like totally confident about these answers. Okay, we'll look at the answers once I finish this section. Taking the relative reactivities of primary, secondary, and tertiary hydrogen atoms into account, what products would you expect to obtain from monochlorination of 2-methylbutane? Of 2-methylbutane. 2-methylbutane. What would the approximate percentage of each product be? Don't forget to take into account the number of each kind of hydrogen. Yeah, so just do this part. So we have 2-methylbutane, 2, 3, 4. Okay, so this is 2-methylbutane. Now, the point is, so we have a tert here, we have a secondary here, and the rest are. So we're going to have 9 primary. We're going to have 2 secondary and 1 tertiary. These are the hydrogen counts. Now, maybe we need to look at the textbook to remember. How did they get this? So we would expect let's just say that like the ratio of reactivity from a tertiary to a primary is 5. And then the ratio of a secondary to a primary is equal to 3.5. Then if we were to convert it all, we have 2 secondaries, so that's equivalent to 7 primary. Then we have 1, we have a tertiary, and then we only have 1. And so that's equivalent to 5 primary hydrogens. So we should expect the ratio to be like 9 to 7 to 5 of the general product of like where they're gonna go. That's kind of my take. Okay. Let's go to the problem 10.3. 1 chloro, 2 methane or methyl, 3 chloro, okay, yeah, I'm pretty sure that's right. There's 5 of them, right? 1, 2, 3, 4, 5. Oh, I didn't write the achiral, but wait, why is it achiral? Oh yeah, it is achiral. It's achiral. It's pretty clear. I think we need to drill into this a little bit more. So we have 1 chloro, 2 meh, bute. This is the first one. We have 2 chloro, 2 meh, bute. That's a second. Okay, we can put it on the third carbon too. This is going to be 2 meh, 3 chloro, bute. I don't know if the name switches around, is it? One chloro, 3 methyl. Yeah, it did switch around. Yeah, it did, and it also went from 2 chloro to 2 meh because the alphabet rule. So now the ratios of these, the percentages of these products that are going to form. Well, let's just draw them all out. So this one is going to be, first we have a butane, we have the methyl group, and then we have a Cl. Here we're going to have the bute, methyl, and the chlorine. So these were primary. This was secondary. And this was tertiary. So what I was predicting is that, so if we add this up, this is 16, this is 21. So 9 out of 21 times you're going to get a primary substitution. That was my prediction. If you use these numbers of like 5 times and 3.5 times. Then similarly for a secondary substitute, you're going to get 1 and 3. Because 7 over 21. And then you're going to get, for a 3 prime, 5 over 21. You're going to get about a, what is that, a 25%? Let's see, was that close even? So the 2, 2. Oh, it was about 25%. So that's pretty good. Then 1 and 4 were both the, wait, 1, 2, 1, 3. This added up to be about 30 plus 15, 45. Let's see, what's 9 over 21? 42. Okay, so I'm actually like pretty close. I don't know why this one would be lower though. My reasoning was that earlier in the book, let's just copy that actually. They said, I looked at, what is it, 2-meth-bute and counted there are 9 prime hydrogens. There's 2 sec H's, and then there's 1 tert H. So the ratio, the equivalent ratios should be 9 to 3.5 times 2 to 5 times 1, which means we expect 9 out of 21 products will be chlorinated on a primary, and 7 out of 21 for sec and 5 out of 21 for tert. But the answer broke it down further, and I'm wondering how we know how we predict that the 2 primary H subs had a factor of 2 difference in percent product. Because it's like this one is a primary hydrogen substitution. 1-chloro, 2-methylbutane. And 1-chloro, 3-methylbutane also, but it's like twice as little. Your method is right. The only thing you skipped is that 2-methylbutane, the primary hydrogen are not all equivalent. There are 2 different primary sites. So primary substitution splits into 2 products. Set A, the 2 CH3 groups attached to C2 the two methyl groups attached to C2 are equivalent by symmetry. Okay, so these are symmetric. And then set B, then this one is distinct. Okay, so if this is like our 1, 2, 3, 4. The C4 primary is different than C1, C1, C5, because those are attached to a tertiary, and this one's attached to a secondary. Okay, so what's the deal? Apply relative react. Given this, compute weighted chances, number of hydrogens times reactivity. So that makes sense. Oh. Oh, I get it now. That's actually really cool. Yeah, because you're going to have like, there's a symmetry in there. Okay, all right. I'm happy with it. Let's keep going. Because there's a lot to do. There's like a lot to do. All right, preparing alkyl halides from alkenes. We've already seen several methods for preparing alkyl halides from alkenes. I haven't, but they have, I guess. Including the reactions of HX and X2 with alkenes in electrophilic addition reactions. The hydrogen halides, hydrochloric acid, hydrobromic acid, hydroiodic acid with alkenes react with alkenes by a polar mechanism to give the product of a Markovnikov addition. So Markovnikov addition, I did this last night. Let me try to figure out. So let's just do like ethylene with HBr. So the double bond attacks the hydrogen because there's a lot of, non-planar electron density sitting above and below the ethylene. This attacks the hydrogen, which is electron deficient, so it's an electrophile, and that causes the bromine to get a lone pair. So that's that. But then you have a carbocation, because then you have this. Actually, these are all H's. Ethylene is just... So then bromine is a minus. And bromine becomes then the nucleophile and attacks the carbocation. So I'm pretty sure that that's how the addition mechanism works. Oh my gosh, I keep clicking on random shit. Okay, bromine and chlorine undergo anti-addition. Oh, so I don't remember any of this stuff. Yeah, the anti and the syn. Okay. Maybe I'll skip this section. It's not that long. Let me just read it. We'll see if we can get through it. Okay, so wait. Let's just start with this right side because I actually understand it. Okay, so we have this like pentene or something, this 1-methylpentene or something, and we react it with, like, let's say hydrobromic acid or something. Now, what's going to happen is that this double bond lone pair, right, because of the planarity of this thing, it's going to have a lot of electron density kind of, because this carbon right here is an sp2 hybridized carbon thing. So there's this pi bond sitting way above. So this pi is going to attack the hydrogen. It's going to push a lone pair onto the X. The X is then, but here's the tricky part. So this forms the carbocation over here, let's say. Let's say that the H gets bonded to this right side where it's tertiary. Okay, you're going to give the hydride shift, though, because you're going to have this, H, C, C, C. But then this is a carbocation. So just instantly this H goes over here, and then the tertiary, the tertiary carbon becomes the carbocation because it's just more stable. Yeah, it's just more stable. So okay, so that's good. So we figured out this hydride shift thing may happen, or it may just be that the electrons kind of immediately attack and connect with this left side. I'm not so sure on that part. Now here we have like chlorine gas or something. Now I'm not too sure about this one. But on the face of it, it kind of makes sense that it's anti because we're going to have a lot of electron density here, and they probably don't want to be on the same side. Another laboratory method for preparing alkyl halides from alkenes is by reaction with N-bromosuccinimide, NBS, in the presence of UV light to give products resulting from the substitution of hydrogen by bromine at the position next to the double bond. The allylic position. See, okay, I'm glad I'm reading this section because that's actually important. And the reason why it's allylic is important is because of the resonance stabilization. I think that's the whole thing. Cyclohexene, for example, gives 3-bromocyclohexene. Why is it 3? Why is this? Because it's like 1, 2. It's right there. Oh, really? Oh, really? Okay, I didn't know that. That's kind of a weird rule. So you have to like go 1, 2, 3, because 1 and 2 have to be okay. That's annoying. But I get it. But there's just a lot of rules. Okay, so let's look here. So we have this what is it? Tetrachloromethane. Is the solvent. We have UV light, and then we have this NBS thing. Okay, and what happens is the allylic bromination. So this allylic bromination with NBS is analogous to the alkane chlorination. But here's my question. Why doesn't this bromine do the same thing as this? That's going to be my question. It occurs by a radical chain reaction pathway. As in alkane halogenation, bromine radical abstracts an allylic hydrogen atom, forming an allylic radical plus HBr. So this carbon is going to be radicalized. The HBr then reacts with the NBS to form bromine gas, which in turn reacts with the allylic radical to yield the brominated product. Wow, that is a very, very convoluted mechanism. Okay, so bromine... So wait, hold on. How does this... So the UV light breaks apart the wait. Allylic bromination with NBS is analogous to the element. Where does the BR radical come from? I think the BR radical must come from this UV light thing. Then HBr reacts. Okay, let's just look at this diagram. Okay, so we steal hydrogen. Now we have a radical carbon, and we formed hydrobromic acid, which is I guess the important thing is there's no water. It's not dissociating. So that's the thing that always has been confusing me lately. Is like you got to actually pay attention now because it's not always just aqueous reactions. Because all of Gen Chem was just aqueous reactions, and that was the only solvent. Okay, so what happens here? It's by this mechanism. So what happens here? There's a lone pair here that attacks the hydrogen. Is that what's happening? Why does bromination with NBS occur exclusively at an allylic position rather than elsewhere in the molecule? The answer is once again found by looking at bond dissociation energies to see the relative stabilities of various kinds of radicals. Although a typical secondary alkyl CH bond has a strength of 410 kilojoules per mole, a vinylic Wait, I thought vinylic was. Wait, I think. I went too far. Although a typical secondary CH bond, a typical vinylic CH bond is weaker. Okay, so wait, secondary. An allylic radical is therefore more stable than a typical alkyl radical with the same substitution. Oh, here we go. Here's a picture. I don't know why I didn't just look at this picture. Alkyl, allylic, vinylic. We can thus expand the stability ordering to include vinylic and allylic radicals. Wait, I think my professor actually said it otherwise. I think he said that it's sort of allylic is kind of in here. So I don't know. How, oh, but this is for radicals. Yeah, I wonder if we had put a methyl here on the allylic, then this would be tertiary. There'd be a hydrogen there, but because what happens in that case? So let me draw cyclohexane, but then we have like a we have 4-methyl cyclohexene. And we're adding let's say like hydrobromic acid. The double bond immediately attacks the H, which pushes the electrons onto here. So now we have okay, I guess this is kind of separate to what we're maybe talking about. There's a lot of concepts to put together. That's the thing. There's a lot of because this radical chemistry is really confusing. No, it doesn't happen. A hydrogen shift only happens So in that case, we should see yeah, 3-methylcyclohexane is the case where a rearrangement can give you a tertiary bromide. Because the methyl-bearing carbon is adjacent to the... Alright. Oh my god, it's so good. Now, you protonate the alkene. Yeah. Okay, I feel like I get that. The radical carbon atom with an unpaired electron can adopt sp2 hybridization, placing the unpaired electron in a p orbital. Is that true, though? The radical carbon atom with an unpaired electron can adopt sp2 hybridization, placing the unpaired electron in a p orbital and giving a structure that is electronically symmetrical. The p orbital on the central carbon can therefore overlap equally with a p orbital on either of the two neighboring carbons. Half of it. Oh, that's okay. Do you have it cut? I'll come over there. Time to lock in. All right, so I'm not getting this allylic radical thing. Because, like, why aren't these sp3 tetrahedral? That's kind of okay. This is my question. The central radical or even carbo even the central radical or even carbocation would be sp2 planar. But the other two carbons, shouldn't they be sp3 tetrahedral? So no resonance? Like, I'm not getting it. Okay, I get it. It's fine. All right, let's just keep moving on because this is taking forever. I got to get to chapter 11. That's the important part. Let's see, how many sections do we have in 10? Okay, so we're like kind of halfway through. Because the allyl radical is electronically symmetrical, it has two resonance forms. One with the unpaired electron on the left, and the double bond on the right, and the other with the unpaired electron on the right and the double bond on the left. Neither structure is correct by itself. The true structure of the allyl radical is a resonance hybrid of the two. As noted, the greater the number of resonance forms, As noted in section 2.5, the greater the number of resonance forms, the greater the stability of a compound, because bonding electrons are attracted to more nuclei. And a low radical with 2 resonance forms is therefore more stable than a typical alkyl radical, which only has a single structure. In molecular orbital terms, the stability of the allyl radical is due to the fact that the unpaired electron is delocalized or spread out over an extended pi orbital network rather than localized only at one site. This delocalization is particularly apparent in the so-called spin density surface, which shows the calculated location of the unpaired electron. The 2 terminal carbons share the unpaired electron equally. In addition to its effect on stability, delocalization of the unpaired electron in the allyl radical has other chemical consequences. Because the unpaired electron is delocalized over both ends of the pi orbital system, reactions with bromine gas can occur at either end. As a result, allylic bromination of an unsymmetrical alkene often leads to a mixture of products. For example, bromination of one octene gives a mixture of 3 bromo 1 octene and 1 bromo 2 octene. Oh, wow. These products are not formed in equal amounts, however, because the intermediate allylic radical is not symmetrical, and reaction at the 2 ends is not equally likely. The products of allylic bromination reactions are useful for conversion into dienes by dehydrohalogenation. Oh, that's a big word. With base. Cyclohexene can be converted into 1,3-cyclohexadiene, for example. So you brominate the allylic carbon, then you add a base. And why does that work? What products would you expect from the reaction of 4,4-dimethylcyclohexene with NBS? Okay, so we were talking about this one actually. Okay, so let me look at it. And we're reacting it with NBS, which is like some similar, NBS is this like pentagonal thing. Where this is an N, this is an H. O. But this is not an H, or it's a Br. It's a bromine. So this is NBS. So I don't actually know what's going on here because Okay, let's see what happens. Strategy: draw the alkene reactant, identify the allylic positions, and identify the allylic position. In this case, there are two different allylic positions. We'll label them A and B. Okay, A and B. Now abstract an allylic hydrogen from each position to generate two corresponding allylic radicals. Each of the two allylic radicals can add a Br atom. Okay, I clearly did not actually understand this mechanism. What happens here? So we end up with just having a radical bromine. Okay, so now we have so this is electrophilic. Or wait, this is nucleophilic. This is nucleophilic. Is that even the right word? I think I have to get my radical and carbo and my not and polar. I think that's the two words. Radical and polar. Okay, but now once we have the this the present alkene gives an allylic radical plus Br. HBr then reacts with NBS to form bromine gas. So how does that happen? This is electrophilic. This is a high electron density. This is nucleophilic, maybe. Okay, so we have a pi, or no, we have a p and a pi. So this dot goes over here, this thing goes over here. Then the same thing here. The dot is here. Wait, the dot goes here and there, then back home. This is a really good problem that I probably am going to skip just because I have a lot of other stuff to do. We're not even really doing the stuff that the class requires, but I just like, I get confused by like the order in which we're doing things. The major product of the reaction of methylene cyclohexane with NBS is 1-bromomethyl cyclohexane. Okay, this sounds cool. So that means that we're going to have Br radicals. And here we have a pi bond. So we're going to have these two are allylic. So what that means is that Br is going to abstract an allylic hydrogen. It could abstract other stuff, but the thing is, it's going to stabilize there. It's much more stable for the radical electron to be resonance stabilized. So what you're going to get is is it the bromine gas or the bromine radicals that then... Okay, I mean, I think it makes sense. Somewhat. Like, parts of it make sense, but we don't have time to do every problem, really. What products would you expect from reaction of the following alkenes with NBS? If more than one product is formed, show the structures of all. So here, you're going to get these two that the... So let's say that the radical bromide, I don't know. It's here. It's stabilized across here, so this pi is kind of all over here. My mic working? Okay, good. Let's just look at the answers because I gotta keep going. So this one was obvious. The intermediate allylic radical. Oh, okay. More accessible. I forgot about that. All right. I'm skipping this one. All right. Preparing alkyl halides from alcohols. Is it really worth reading this? I think we probably should just skip to chapter 11. Okay, nucleophilic substitution and base-induced elimination are two of the most widely occurring and versatile reactions in organic chemistry, both in the laboratory and in biological pathways. We'll look at them closely in this chapter to see how they occur, what their characteristics are, and how they can be used. We'll begin looking at substitution reactions. As we saw in the preceding chapter, that the carbon halogen bond in an alkyl halide is polar and that the carbon atom is electron poor. Thus, alkyl halides are electrophiles. And much of their chemistry involves polar reactions with nucleophiles and bases. Alkyl halides do one of two things when they react with a nucleophile, or a base, such as a hydroxide ion. They either undergo substitution of the X group by the nucleophile, or they undergo elimination of HX to yield an alkene. So you have bromoethane and a hydroxide ion. The hydroxide ion is nucleophilic. The discovery of nucleophilic substitution reactions dates back to work carried out by the German chemist Paul Walden in 1896. Walden found that the pure enantiomeric plus and minus malic acids would be interconverted through a series of simple substitution reactions. When Walden treated minus malic acid with uh, At the time, the results were astonishing. The eminent chemist M.L. Fisher called Walden's discovery the most remarkable observation made in the field of optical activity since the fundamental observations of Pasteur. Because minus malic acid was converted into plus malic acid, some reactions in the cycle must have occurred with a change or inversion of configuration at the chirality center. But which ones and how? Remember that the direction of light rotation and the configuration of a chirality center aren't directly related. You can't tell by looking at the sign of rotation whether a change in conformation has occurred. Today we refer to the transformations taking place in Walden's cycle as nucleophilic substitution reactions because the step involves the substitution of one nucleophile, chloride ion, or hydroxide ion, by another. Nucleophilic substitution reactions are one of the most common and versatile reaction types in organic chemistry. Following the work of Walden, further investigations were undertaken in the 1920s and 30s to clarify the mechanism of nucleophilic substitution reactions and to find out how inversions of configuration occur. Among the first series studied was one that interconverted the two enantiomers of 1-phenyl-2-propanol. 1-phenyl-2-propanol. Okay, 1-phenyl. Is it like that? Oh, I did this wrong. I did it wrong. Oh, wait. 1-phenyl, 2 oh, shit. Okay. This was one that interconverted the two enantiomers of 1-phenyl-2-propanol. Exactly the same type of reaction is involved. What the hell are we looking at? In the three-step reaction sequence shown, plus 1-phenol 2-propanol is interconverted with its minus enantiomer. So at least one of the three steps must involve an inversion of configuration at the chirality center. Step 1. Formation of a tosylate occurs by breaking the OH bond of the alcohol rather than the CO bond to the chiral carbon. So the configuration around the carbon is unchanged. Yeah. Similarly, step 3, hydroxide ion cleavage of the acetate hydroxide ion cleavage takes place without breaking the CO bond at the chirality center. How does this flip? Oh, okay, yeah. In step 3, I was looking at step 2 and I was getting so confused. Thus, the inversion of stereochemical configuration must take place in step 2, the nucleophilic substitution of tosylate ion by acetate. All right, we're getting somewhere now. We're freaking getting somewhere now. So what happens? Now that's the question. From this and nearly a dozen other series of similar reactions, researchers concluded that the nucleophilic substitution of a primary or secondary alkyl halide or tosylate always proceeds with inversion of configuration. Tertiary alkyl halides and tosylates, as we'll see shortly, give different stereochemical results and react by a different mechanism than the primary and secondary ones. Okay. Predicting the stereochemistry of a nucleophilic substitution reaction. What product would you expect from a nucleophilic substitution of an R1-bromo phenylethane? 1-bromo 1-phenylethane with cyanide ion as nucleophile. Okay. One bromo, 1-phenylethane plus C minus N lone pair. Yep, this is R. Because bromine wins. You look down the HC bond, bromine wins as group 1. So then this is obviously group 2. There's more carbons here. So this is like a counterclockwise. So then you flip it. It's clockwise. It's R. Draw the R enantiomer of the reactant. Then change the configuration of the chirality center while replacing Br with this. So we're going to have what product would you expect from a nucleophilic substitution of S2-bromohexane? Okay, so let's first off, we're going to, with acetate ion. Assume that the inversion of configuration occurs and show the stereochemistry of both the reactant and product. Okay, this was pretty easy because they tell you, hey, the configuration is going to invert. So first we're going to draw 2-bromohexane. Actually, let's just do this thing. I like doing this. I mean, it's not easy all the time, but in general, it's kind of fun. Okay. Let me just finish this yogurt. Okay, so the S is going to be no wait, I did it wrong. No, wait, no, I did it right. Fuck. Because you look down the HC bond, then this is group 1, this is group 2. So now we have an, HC is C clock. So then C to H is clock. Oh, no, this is clockwise. And this is C clock. Holy crap. Oh god. You look down HC. Then you get an R. That doesn't exactly do it the way that I want. But imagine that when I flipped it like this, so the BR is coming out at the page. It's S. Okay, this is S. I'm almost positive. Okay. Okay, so now we have the thing. Now we want to add acetate ion. So, okay, wait, let me just think about what is it that they expect us to come up with. It's probably going to be No, this is wrong. I know this is wrong. This has to be wrong because this is an R. Oh, wait, no. This is an R. This is good. Bro, it's so easy to get the freaking stereochemistry mixed up. Which problem are we doing right now? 11-1. One methyl pentyl acetate. Okay, I think they're just trying to warm us up, but Jesus. Okay, the SN2 reaction. We're finally I don't know. In almost all chemical reactions, there's a direct relationship between the rate at which the reaction occurs and the concentrations of the reactants. When we measure this relationship, we measure the kinetics of the reaction. For example, let's look at the kinetics of a simple nucleophilic substitution. The reaction of bromomethane with hydroxide to yield methanol. With a given temperature, solvent, and concentration of reactants, The substitution occurs at a certain rate. If we double the concentration of OH-, the frequency of encounters between reaction partners the reaction rate doubles. Similarly, if we double the concentration of the bromomethane, the reaction again doubles. A mechanism that accounts for both the inversion of configuration and the second order kinetics that are observed with nucleophilic substitutions was suggested in 1937 by Ingold. Wait, no, never mind. Bimolecular means that the two molecules nucleophile and alkyl halide take part in the step whose kinetics are measured. The essential feature of the SN2 mechanism is that it takes place in a single step, without intermediates. When the incoming nucleophile reacts with the alkyl halide or tosylate, the substrate, from a direction opposite the group that is displaced, the leaving group, the essential feature of the SN2 mechanism is that it takes place in a single step without intermediates. When the incoming nucleophile reacts with the substrate from a direction opposite the group that is displaced. As the nucleophile comes in on one side of the substrate and bonds to the carbon, the halide or tosylate departs from the other side, thereby inverting the stereochemical configuration. The process is shown for S2-bromobutane. So we have the nucleophile uses OH-. Wait, no. The nucleophile, hydroxide, uses its lone pair electrons to attack the alkyl halide carbon 180 degrees away from the departing halogen. This leads to a transition state with a partially formed OH bond and a partially broken CBr bond. The stereochemistry at carbon is inverted as the COH bond fully forms and the bromide ion departs with the electron pair from the former CBr bond. As shown in figure 11.4, the SN2 reaction occurs when an electron pair on the nucleophile forces out the group X-, which takes with it an electron pair from the former CX bond. This occurs through a transition state in which the new C bond, the new nucleophile carbon bond, is partially formed at the same time the old carbon X bond is partially broken. and in which the negative charge is shared by both the incoming nucleophile and the outgoing halide ion. The transition state for this inversion has the remaining 3 bonds in a planar arrangement. Oh, this is a freaking awesome picture. Oh, this is awesome. Oh, that's so cool, actually. All right, this picture is like my favorite picture we've seen today. The transition state of an SN2 reaction has a planar arrangement of the carbon atom and the remaining 3 groups. Electrostatic potential maps show that the negative charge is delocalized in the transition state. The mechanism proposed by Hughes and Ingold is fully consistent with experimental results, explaining both stereochemical and kinetic data. Thus, the requirement for a backside approach of the entering nucleophile causes the stereochemistry of the substrate to invert, much like an umbrella turning out inside out in the wind. That's a good metaphor, actually. I like that metaphor. It's the umbrella. The Hughes-Ingold mechanism also explains why second-order kinetics are observed. The SN2 reaction occurs in a single step that involves both the alkyl halide and nucleophile. Two molecules are involved in the step whose rate is measured. Oh, yeah. All right, problem 11-2. What product would you expect to obtain from an SN2 reaction of hydroxide with R2-bromobutane? Oh, yeah. Do you need it? I don't have to use it. Yeah, use it for as much time as you want. Okay, no iPad. Let's just do the problem. It's actually better. What product would you expect to obtain from the SN2 reaction of hydroxide? So we have HO minus plus. Okay, so first off, let's draw some 2-bromobutane. So we want it to be R. So then this is going back. Okay. So R2-bromobutane is wedge on the BR and a dash on the H. So now what's going to happen is this lone pair is going to come in onto here and push this lone pair onto BR. And we're going to get This H is a wedge. I gotta draw this one. How did they do it? So they had CH3 dashed to C, which is wedged to H. Wait, what? This isn't S? Oh, wait. No, this is S. And then this is R. Okay. They're kind of pushed up. Maybe these are like slightly wedged or something. Yeah, this problem is actually really hard. It's hard because it's hard to visualize the umbrella flipping. So if I want to do it one last time. So it's the R, so this is H, and this is BR. I want to see the answer to that one, but let's do 11.3 now. Assign configuration to the following substance. Assign configuration to the following substance and draw the structure of the product that would result from a nucleophilic substitution with HS. Okay, so this is going to be S. So it's the reactant configuration is S. First, let's name it. 1, 2, 3, 4, 5. 2 bromo 4 methyl pentane. So first off, it's 2 bromo 4 methyl pentane. Okay, so we have Br coming out at us, and it's an R. Wait, no, is it an R? No, it's an S. So what's gonna happen is with HS. Okay, let's look at the answers to this in the book. So problem 11.2, it just says S2-butanol.
Stereochemistry of SN2 reaction. SN2.
I need animations. This one's pretty good though. Why was it so fast and now it's so slow? If this is group 2 right here. Ooh, whoa, that's cool. Damn, this is cool, dude. Okay, all right. So imagine this carbon is the primary 2 carbon and the leaving group is also that. Then this configuration is going to be R if that back, well, if the back, let's just imagine the back one is hydrogen. I think that's the easiest thing. So we're looking down at it and we're trying to figure out if it's clockwise or counterclockwise. Then no matter what, even before and after, you can draw this. This is going to be R if this is the second group. But then here, this is going to flip and now this is going to be S. So it goes from R to S. Okay, so what's going to happen here is that maybe it's easier to actually imagine it. Oh, imagine it's coming from the back of the page. Okay, then this bromide leaves. Okay, so now this thing gets pushed over here. Okay, I got it. I know how to draw these things now. So instead of drawing it from there, you draw it going into there. And then you have this H gets pushed this way. So then this comes out of the page, and now you have the OH going back. And now you can see that this is S. And this was R. Good. Okay. All right. I actually feel like it kind of makes sense now. You imagine it going from the back, bro. Instead of having it go from here, which is confusing, you want to actually visualize it going from 180 degrees from the leaving group, which is what they say, but like you actually have to do it that way. Otherwise it makes no sense. like these two aren't going to move very much, but this one is the one that's going to shift kind of in this perspective. Characteristics of the SN2 reaction. Now that we know how SN2 reactions occur, we need to see how they can be used and what variables affect them. Some SN2 reactions are fast and some are slow. Some take place in high yield and others in low yield. Understanding the factors involved can be of tremendous value. Let's begin by recalling a few things about reaction rates in general. The rate of a chemical reaction is determined by the activation delta G star. I don't know what you call that thing. If I even copy and paste that character, what do I get? Oh, what is this called? DAG or OB. Delta G dagger. The energy difference between the reactant ground state and the transition state. A change in reaction conditions can affect the activation energy either by changing the reactant energy level or by changing the transition state energy level. Lowering the reactant energy or raising the transition state energy increases the activation energy and decreases the reaction rate. Raising the reactant energy or decreasing the transition state energy decreases the activation energy and increases the reaction rate. We'll see examples of all these as we look at SN2 reaction variables. So in this case, we are raising the reactant energies, and here we are lowering the activation energy. The reactant energy, okay. Steric effects in the SN2 reaction. The first SN2 reaction variable to look at is the structure of the substrate. Because the SN2 transition state involves partial bond formation between the incoming nucleophile and the alkyl halide carbon atom, it seems reasonable that a hindered, bulky substrate should prevent easy approach of the nucleophile, making bond formation difficult. In other words, the transition state for reaction of a sterically hindered substrate, the transition state for reaction of a sterically hindered substrate whose carbon atom is shielded from the approach of the incoming nucleophile is higher in energy and forms more slowly than the corresponding transition state for a less hindered substrate. Okay, yeah, I don't know why I was pausing. Steric hindrance in SN2. As the models indicate, the carbon atom in bromomethane is readily accessible, resulting in a fast SN2 reaction. The transition state energy for sterically is higher in energy than less Hindered. Okay. As figure 11.7 shows, the difficulty of nucleophile approach increases as the three substituents bonded to the halo-substituted carbon increase in size. Methyl halides are by far the most reactive substrates in SN2 reactions, followed by primary, such as ethyl and propyl. Alkyl branching at the isopropyl halides. Okay, yeah. Secondary. And TERT basically halts the reaction. Even branching one carbon away from the reacting center, as in 2,2-dimethylpropyl halides. Alright, so wait, hold on. 1,3-dimethyl. And this is going to be X. So this is the carbon, but the thing away from it. Okay. Greatly hinders nucleophilic displacement. As a result, SN2 reactions occur only at relatively unhindered sites and are normally useful only with methyl halides, primary halides, and a few simple secondary halides. Vanillic halides and aryl halides are not shown on this reactivity list because they are unreactive toward SN2 displacement. This lack of reactivity is due to steric factors. The incoming nucleophile would have to approach in the plane of the carbon-carbon double bond. The plane of the carbon-carbon double bond and burrow through part of the molecule to carry out the backside displacement. All right, the nucleophile. Another variable that has a major effect on the SN2 reaction is the nature of the nucleophile itself. Any species, either neutral or negatively charged, can act as a nucleophile as long as it has an unshared pair of electrons. That is, as long as it is a Lewis base. If the nucleophile is negatively charged, the product is neutral. If the nucleophile is neutral, the product is positively charged. A wide array of substances can be prepared using nucleophilic substitution reactions. In fact, we've already seen some examples in previous chapters. For instance, the reaction of acetylide ion with an alkyl halide is an SN2 reaction in which the acetylide nucleophile displaces a halide leaving group. Okay, cool. Table 11.1 lists some nucleophiles in the order of their reactivity, shows the products of their reactions with bromomethane, and gives relative rates of their reactions. There are large differences in the rates. So water is a pretty terrible SN2 nucleophile. Water is a terrible SN2 nucleophile. Why is water terrible? Water is strongly solvated. Oxygen is small and very polar. So in a protic solvent, like water, it gets wrapped in tight H bonding shells. Okay, so it's those solvation shells. To attack the carbon, water has to shed some of that solvation, which costs energy, lower nucleophilicity. Okay, so it's largely stabilized by the solvent itself. But what if it wasn't in a... That's why nucleophilicity trends in protic solvents. Water is neutral, not very electron rich, and becomes a cation after attack. In SN2, nucleophile donates a pair into sigma star and forms a bond. If H2O attacks, the immediate product is oxonium. Then it must deprotonate. Neutral nucleophiles are generally weaker than anions. OH minus or HO minus is a much better SN2 nucleophile than water. RS is even better. So water has lone pairs, but they're tied up by solvation. Okay. What are the reasons for the reactivity differences observed? Why do some reactants appear to be much more nucleophilic than others? The answers to these questions aren't straightforward. Part of the problem is that the term nucleophilicity is imprecise. The term is usually taken to be a measure of the affinity of a nucleophile for a carbon atom in the SN2 reaction. But the reactivity of a given nucleophile can change from one reaction to the next. The exact nucleophilicity of a species in a given reaction depends on the substrate, the solvent, and even the reactant concentrations. But some trends can be detected from the data. Nucleophilicity roughly parallels basicity. Basicity. What did I say? What the hell did I just say? When comparing nucleophiles that have the same reacting atom. Thus, OH minus is more basic and nucleophilic than acetate ion. Because this conjugate acid is really weak. Water, super weak acid. But the conjugate acid of acetate is pretty strong, relatively. Which in turn is more basic and more nucleophilic than water. Bro, oh my god. Why do I always do this? How long has it been going on like that? I gotta just leave it on. I think actually I gotta just stop using this button. Can't believe I did that. I've been talking for like an hour. Whatever. Unlike what occurs where the leaving group is displaced. Unlike what occurs in an SN2 reaction where the leaving group is displaced while the incoming nucleophile approaches, an SN1 reaction takes place by loss of the leaving group before the nucleophile approaches. 2-bromo-2-methylpropane spontaneously dissociates to the tert-butyl carbocation plus Br- in a slow rate-limiting step, and the intermediate carbocation is then immediately trapped by the nucleophile water in a faster second step. Thus, water is not a reactant in the step whose rate is measured. Dude, I can't stop thinking about this carbocations are planar sp2 hybridized in achiral. Thus, if we were to carry out an SN1 reaction on one enantiomer of a chiral reactant and go through an achiral carbocation intermediate, the product loses its optical activity. That is, the symmetrical intermediate carbocation can react with a nucleophile equally well from either side, leading to a racemic 50-50 mixture of enantiomers. So we get so this dissociates, that's the first step. It's the rate determining step. Then we have a planar carbocation. Now the nucleophile could approach from either side, and this is the retained chiral configuration, and this is the inversion of configuration. Because the reaction goes through an achiral intermediate, an enantiomerically pure reactant gives an optically inactive in theory. The conclusion that SN1 reactions on enantiomerically pure substrates should give racemic products is nearly, but not exactly, what is found. In fact, few SN1 displacements occur with complete racemization. Most give a minor 0 to 20% excess of inversion. So what is that, 50-50 to 70-30? Yeah. The reaction of R6-chloro-2,6-dimethyl octane with water, for example, leads to an alcohol product that is approximately 80% racemized. Wait, what? I think this is supposed to say oh, that is so weird. Why would they write it like that? Yeah, 60-40. This lack of complete racemization in SN1 reactions is due to the fact that ion pairs are involved. According to this explanation, first proposed by Saul Winston at UCLA, dissociation of the substrate occurs to give a structure in which the two ions are still loosely associated, in which the carbocation is effectively shielded from reaction on one side by the departing anion. If a certain amount of substitution occurs before the two ions fully diffuse apart, a net inversion of configuration will be observed. Okay, what products would you expect from the reaction of S3-chloro 3? Okay, 3-chloro-3-methyl octane. So 11-8. So we have octane, and then 3-chloro-3-methyl. So first off, it's a tertiary carbon with a leaving group. And so SN2 is just not going to happen. So then we have to go through an intermediate where we have 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7, 8. So then now we have a plus here, a Cl minus, and there is a hydrogen still there. So presumably it's gonna do inversion because you're gonna have that effect. So you're gonna get R. It's reaction with acetic acid. Okay, I'm gonna say that you're gonna get a decent bias towards inversion. Okay, among the many examples of SN1 reactions that occur with incomplete racemization, the optically pure tosylate of 2,2-dimethyl, 1-phenyl, 1-propanol, Let's see if we can write that. So we got propanol. So let's do 1, 2, 3, all OH minus. Then we have a 1-phenyl. Two 2,2-methyl, 1-phenyl, one. Oh wait, I got it. Okay. Okay, I got it right. I don't even know how to do this problem. They didn't even explain that. One phenyl, one bromo, one bromo, one phenyl. Can you make the chain out? Or I guess the chain has to, I'm pretty sure the chain has to start with the phenyl group. So it's going to be one bromo, one methyl, one phenyl, propane. Okay, the stereo is going to be 1, 2, 3. So this is the last group, this methyl group. So we're looking down at, this is an S. But it's this huge tertiary carbon. So I would expect S. or at least pretty racemic. Why? All right. All right. Where are we at here? Okay, so characteristics of the SN1 reaction. Just as the SN2 reaction is strongly influenced by the structure of the substrate, the leaving group, the nucleophile, and the solvent. The substrate, the leaving group, the nucleophile, and the solvent. The SN1 reaction is similarly influenced. Factors that lower the activation energy either by lowering the energy level of the transition state or by raising the energy level of the ground state favor faster SN1 reactions. Conversely, factors that raise the activation energy either by raising the energy level of the transition state or by lowering the energy level of the reactant slow down the SN1 reaction. The substrate. According to the Hammond postulate, any factor that stabilizes a high energy intermediate also stabilizes the transition state leading to that intermediate. Because the rate-limiting step in an SN1 reaction is the spontaneous unimolecular dissociation of the substrate to yield a carbocation. The reaction is favored whenever a stabilized carbocation intermediate is formed. The more stable the carbocation intermediate, the faster the SN1 reaction. We saw in 7.9 that the stability order of alkyl carbocations to this list, we should also add the resonance-stabilized allyl and benzyl cations. Just as allylic radicals are unusually stable because the unpaired electron can be delocalized over the extended pi orbital system, so allylic and benzylic carbocations are unusually stable. The word benzylic means next to an aromatic ring. As 11.13 indicates, an allylic cation has two resonance forms. In one form, the double bond is on the left. In the other, it's on the right. A benzylic cation has 5 resonance forms, all of which contribute to the overall resonance. That's pretty cool, actually. So what is that saying? That's saying that the carbocation is stabilized. So that means that this makes this structure with a leaving group on it makes for a very good SN1 substrate because it's so stabilized. Its carbocation is so stabilized that like it's not like this burning white hot flame trying to react with something as much. The positive charge is delocalized over the pi system in both. Electron poor atoms indicated by blue arrows. Oh yeah. But like they're all sharing it. Because of resonance stabilization, a primary allylic or benzylic carbocation is about as stable a primary benzylic carbocation is about as stable as a secondary alkyl carbocation. Right, the stability of the carbocation. Okay. The stability order of carbocations is the same as the order of SN1 reactivity for alkyl halides and tosylates. We should note parenthetically that primary allylic and benzylic substrates are particularly reactive in SN2 reactions as well as SN1 reactions. Yeah, that's what I was thinking about. Allylic and benzylic CX bonds are about 50 kilojoules per mole. Wait, what does that mean? Okay. Okay, I think that makes sense. Now let's rank the following substances in order of their expected SN1 reactivity. The carbocation is not going to be very stable here, so this should be pretty weak. Here, the carbocation is allylic. It's a second degree allylic. So this is going to be the best. This is tricky because in this case we have a primary. Oh wait, no, but this is. I'm pretty sure this is vinylic, not allylic. So I would assume that this is not a very good leaving group. So I'm going to say that the best is 2, which is then then 4, then 1, then 3. Honestly, I'm not too sure about this one. Okay, so I was right, but I don't know how you're supposed to know the difference between the last two. Let's just see if this thing gets it right. Because I don't even know if it understands what molecules. Yeah, the vanillic is, yeah. Cool. All right. So I basically did get it, that this was vanillic and that's why it's last. We gotta hurry up. 3 bromo, 1 butene. So, okay, wait. Okay. 3 bromo, 1 butene. And 1 bromo, 2 butene. Wait, what does this look like? What the hell is that? Wait, that doesn't even look right. 1, 2. Oh yeah, okay, that's what I have. But that rendering got messed up, man. What's up with that rendering, bro? Undergo the SN1 reaction at nearly the same rate, even though one is a secondary halide and the other is primary. It's that this one has allylic carbocation, but this one is secondary. This is a primary allylic versus a secondary, so they're about the same. So that's what they're trying to get at. All right, the leaving group. We said during the discussion of SN2 reactivity that the best leaving groups. Okay, wait, hold on. Before it answers, let me try to finish the sentence. The best leaving groups for SN2 are those that are pretty stable anions. That is, those that are conjugate bases of strong acids. An identical reactivity order is found for the SN1 reaction because the leaving group is directly involved in the rate limiting step. So leaving group reactivity is water's the best. Then we have like iodine and tosyl oxide or some shit. Then note that in the SN1 reaction, which is often carried out under acidic conditions, neutral water is sometimes the leaving group. This occurs, for example, when an alkyl halide is prepared from a tertiary alcohol by reaction with HBr or HCl. As shown in figure 11.14, the alcohol is first protonated and then spontaneously loses water to generate a carbocation, which reacts with a halide ion to give the alkyl halide. Knowing that an SN1 reaction is involved in the conversion of alcohols to alkyl halides explains why the reaction works well only for tertiary alcohols. Tertiary alcohols react fastest because they give the most stable carbocation intermediates. Yeah, okay, so yep, that actually, this one's like really easy to understand, I think. The nature of the nucleophile plays a major role in the SN2 reaction. It's easy to read the words and very hard to understand them. The nature of the nucleophile in SN1 reactions, or the nature of the nucleophile plays a major role in the SN2 reactions, but does not affect an SN1 reaction. Because the SN1 reaction occurs through a rate-limiting step in which the added nucleophile has no part, the nucleophile can't affect the reaction rate. The reaction of 2-methyl, 2-propanol with HX, for instance, occurs at the same rate regardless of whether the X is Cl, Br, or I. Furthermore, neutral nucleophiles are just as effective as negatively charged ones. So SN1 reactions frequently occur under neutral or acidic conditions. That's weird. The rate is controlled by making the carbocation after OH is protonated and leaves as water. This step doesn't care much about whether the nucleophile present, but which product you end up with does depend on what happens after the carbocation forms. If they're all together, the carbon can be trapped by any of them, but who wins depends mainly on nucleophilicity in a protic acidic medium like HX alcohol solution. I is the best nucleophile, then Br, then Cl, because I is the largest and most polarizable and least strongly solvated. Okay, cool. What about the solvent? Do solvents have the same effect in SN1 reactions as they do in SN2 reactions? The answer is both yes and no. Solvents have a large effect on SN1 reactions, but no, the reasons for the effects on SN1 and SN2 reactions are not the same. Okay, wait. What were the solvent effects? It was that if you had the protic polar solvents in SN2, the problem is that the nucleophile, which is needed to kick off the leaving group, has been stabilized, electronically, and has a lower energy. So that means that the activation energy to sort of break through all of the solvation effects and actually hit the backside attack is it's much more unlikely. Okay, so that all checks out, and I feel like I could remember that. Solvent effects in the SN2 reaction are due largely to stabilization or destabilization of the nucleophile reactant, while solvent effects in the SN1 reaction are due to largely to stabilization or destabilization of the transition state. The Hammond postulate says that any factor stabilizing the intermediate carbocation should increase the rate of an SN1 reaction. I don't really get it. Solvation of the carbocation. The interaction of the ion with solvent molecules has such an effect. Solvent molecules orient around the carbocation so that the electron-rich ends of the solvent dipoles face the positive charge, thereby lowering the energy of the ion and favoring its formation. The properties of a solvent then contribute to its ability to stabilize ions by solvation are related to the solvent's polarity. SN1 reactions take place much more rapidly in strongly polar solvents, such as water and methanol, than in less polar solvents, such as ether and chloroform. In the reaction of 2-chloro-2-methylpropane, for example, a rate increase of 100 K is observed upon going from ethanol to water. What does this even mean, dude? Obviously, you should be able to measure that. SN2 reactions are disfavored by protic solvents because the ground state energy of the nucleophile is lowered by solvation. SN1 reactions are favored in protic solvents because the transition state of energy leading to carbocation because the transition state energy leading to carbocation intermediate is lowered by solvation. Okay, so how does the substrate impact SN1 reactions? Start back. What is SN1? It's that a leaving group spontaneously leaves, and it takes with it an electron pair, forming a planar carbocation. Okay, so the substrate needs to be stable. So we're going to prefer, like allylic, benzylic, but this is not even as important as like, tertiary, things that can stabilize the carbocation intramolecularly. So the best substrates yields the most stable carbocations. Tertiary, allylic, and benzylic. Bro, I didn't even read that and I just knew. I'm getting ready. I'm heating up. Heating up. All right, leaving group. Okay, so what leaving group is going to be good? Well, it's something that, I don't know if we talked about. Does it get solvated? Can its energy be brought down through solvent effects? Because that could be one thing. But I think it's the same as in SN2. It's that anything that is able to hold the ionic charge. Good leaving groups increase the reaction rate by lowering the energy level of the transition state. Transition state. What does that actually mean, though? We said that the best leaving groups are those that are most stable. That is, whose conjugate bases I'm gonna take a walk around the block. Take a short walk. I have so much work to do. Predict whether the following substitution reactions are likely to be SN1 or SN2. Secondary benzylic. This has got to be SN1, bro. Okay, wait, but let's look at everything that's going on. It's being done in acetic acid and water, and so we're reacting with acetate, and we're getting we got to think energetically. So the shit. The lone pair on the oxygen in an SN2 is going to tack here. And then this is going to go on to Cl minus. Okay, so starting off, we have steric hindrance preventing the backside attack. Now let's consider the nucleophile. Is this a good nucleophile? What makes a good nucleophile? Well, we're doing it in water, which is a protic polar solvent, so it's already being solvated. So what we're doing there is increasing the activation energy, and and we're lowering the ground state energy. That's what we're doing. So then this is going to need a lot of energy to hit this thing, enough to get in there. It's also pretty big itself. I don't know if they didn't really talk about that, but I feel like that's gotta matter. If you're talking about steric hindrance and you're worried about a couple of methyl groups here, then you should be worried about a couple of methyl groups here too. Okay, so what do we have? We have substrate, leaving group, nucleophile, and solvent. What makes a good SN2 nucleophile? Something with higher energy. That's kind of all it said. Negatively charged. It is negatively charged. I'm going to say this is almost certainly SN1. But I want to treat the problem like it's hard. Okay, here we go. We have... It's a primary carbocation. CH3O. This is meth oxide. And we're doing it in DMF. Polar, protic. Is it? Okay, so it's aprotic. So that means that we don't have solvation effect. So, okay, wait. We got to start off. One, we're looking at the substrate. Is it sterically hindered? It's a primary carbocation. So that's pretty good. We can do that. Now let's look at the... What is the order in which I should be thinking about these? Maybe the next one we'll just say is the nucleophile. So the nucleophile, pretty small, negatively charged. No problems there, I think. Okay, now we're going to look at the leaving group. Leaving group is a halogen. Bromide, pretty big. Big. Okay, for SN2. Okay, now the fourth one is the solvent. And no OH or NH bonds, but has, what is it, C double O? Is it C double O? Yeah. So it is polar. Thus, we're not going to have as many solvation effects So I think that we're pretty good. I think that this is almost certainly SN2. Look at the substrate, leaving group, nucleophile, and solvent. Then decide from the summaries at the ends of sections 11.3 and 11.5 whether an SN1 or SN2 is favored. SN1 reactions are favored by tertiary allylic or benzylic, by good leaving groups, non-basic nucleophiles, and by protic solvents. All right, 1113. Predict whether each of the following substitutions is SN1 or SN2. This is interesting. Our leaving group is hydroxide. But here, this is going to be allylic. But also, it's a secondary carbocation, secondary allylic carbocation. Okay, but it's being treated in a protic solvent. And it's being treated with HCl. It's going to be in an acidic environment. This is going to... I know it's going to be SN1, but there's too many, like... The reason it's SN1 is this thing immediately is just too sterically hindered for backside attack. Which would be that a lone pair from Cl comes in here. All right, let's look at this one. Okay, we're doing it in a polar aprotic environment. This is a primary allylic. So hold on. So let's write A is the carbon is secondary allylic in protic polar solvent. All I wrote is the carbon is a secondary allylic in a protic polar solvent, so it's unlikely to be SN2. Here we have a primary allylic. But what does allylic actually do? Now, see, sometimes I feel like I get it and then I lose it all. Like, what are we talking about here? A primary benzylic may be stabilized, might stabilize the carbocation enough, meaning substrate nucleophile leaving group. Oh, no. For some reason, the leaving group doesn't matter that much. No, it's solvent. Okay, so here we got a secondary and a protic salt. Secondary, the nucleophile is a strong acid, but it's not negative. I'm gonna guess this is SN1. Also, okay, so this one's a tertiary. So it's got to be SN1. Wait, no. This carbon is not a tertiary. It's a primary. This is a primary allylic. So primary allylic could be SN1. Aprotic solvent. I don't know how to assess that leaving group. But it's negative. This is SN2. SN1, SN2. Okay. Biological substitution reactions. Both SN1 and SN2 reactions are common in biological chemistry, particularly in the pathways for biosynthesis of many thousands of plant-derived substances called terpenoids. Unlike what typically happens in the laboratory, however, the substrate in a biological substitution reaction is usually an organodiphosphate rather than an alkyl halide. Thus, the leaving group is the diphosphate ion PPI rather than a halide ion. In fact, it's useful to think of the diphosphate group as the biological equivalent of a halide. The dissociation of such an organodiphosphate in a biological reaction is typically assisted by the complexation to a divalent metal cation such as magnesium to neutralize charge and make the diphosphate a better leaving group. As an example, two SN1 reactions occur during the biosynthesis of geraniol, a fragrant alcohol found in roses and used in perfumery. Geraniol biosynthesis begins with dissociation of dimethyl allyl diphosphate to give an allylic carbocation, which reacts with isopentyl isopentenyl. Isopentenyl diphosphate. From the viewpoint of isopentenyl diphosphate, the reaction is an electrophilic alkene addition. Biological substitution reactions. Should I skip this? Okay, this is what I need. We need this because my teacher definitely covered this. Elimination reactions. Zaitsev's rule. We said at the beginning of this chapter that two kinds of reactions can take place when a nucleophile Lewis base reacts with an alkyl halide. The nucleophile can either substitute for the halide by reaction at carbon or can cause an elimination of HX at a neighboring hydrogen. Elimination reactions are more complex than substitution reactions for several reasons. One is the problem of regiochemistry. What product results by loss of HX from an unsymmetrical halide? In fact, elimination reactions almost always give mixtures of alkene products. And the best we can usually do is predict which will be the major product. According to Zaitsev's rule, base-induced elimination reactions generally, although not always, give the more stable alkene product. That is the alkene with more alkyl substituents on the double bond carbons. In the following two cases, for example, the more highly substituted alkene product predominates. In the E1 reaction, the CX bond breaks first to give a carbocation intermediate, which undergoes subsequent base subtraction of H plus to yield the alkene. What product would you expect from the reaction of 1-chloro-1-methylcyclohexane with KOH and ethanol? How might we know? So this has got to be our leaving group. And it's a tertiary carbon. So SN2 is not going to happen. SN1 could happen. This just leaves. And then an OH goes onto here. Maybe. Treatment of an alkyl halide with a strong base yields an alkene. Okay, so I wish they would draw more arrows. I need the arrows, bro. I don't know what the heck is going on here. Define the products in a specific case. Locate the hydrogen atoms on each carbon next to the leaving group. Then generate the potential alkene products by removing HX in as many ways as possible. The major product will be the one that has the most highly substituted double bond. So this double bond has 1, 2, 3. This double bond has... Wait. 1, 2, 3. 0, 1, 2. Okay. Ignoring double bond stereochemistry, what products would you expect from elimination reactions of the following alkyl halides? Here we have pentane, 2-methyl 3-bromo, 2-methyl 3-bromo. I always forget. Do you do? Oh yeah. I feel like that rule is so weird. Like, why do they have that rule where you alphabetize it? What's the point of that? Why not do it by substituent number? Okay, I did A. Let's use the iPad. What problem was this? Yeah, I skipped all these. Bro, why don't they draw them, man? It's so annoying. Two methyl, two pentene. And then minor is 4 methyl, 2 pentene. Okay. The major product is the two, three, 5 methyl. 1, 2, 3, 4, 5, 6. 2 hexene. Yeah, that's right. Ethylide. Ethyl iodine cyclohexane. Bro, I don't know what that is. Okay. What alkyl halides might the following be made from? What does that even mean? Man, it's a beautiful day. For instance, the base-induced elimination of HBr from 1-bromo-2-pentyl phenylethyl Of the two, anti-paraplanetary energy I need to take a break. What the hell are we talking about now? Okay. What's so special about periplanar geometry? Because sp3 sigma orbitals in the reactant CH and CX bonds must overlap and become p pi or in the alkene. Okay. Draw. That's silly. P pi. There must also be some overlap in the transition state. This can occur most easily if all the orbitals are in the same plane to begin with. That is, if they're periplanar. Overlap of the developing p orbitals in the transition state requires periplanar geometry. You can think of E2 elimination reactions with periplanar geometry as being similar to SN2 reactions with 180-degree geometry. In SN2, an electron pair from the incoming nucleophile pushes out the leaving group on the opposite side of the molecule. In E2, an electron pair from a neighboring CH bond also pushes out the leaving group on the opposite side of the molecule. Okay. Anti-periplanar geometry for E2 eliminations has specific stereochemical consequences that provide strong evidence for the proposed mechanism. To take one example, 1,2-dibromo-diphenylethane undergoes E2 elimination on treatment with base to give only the E alkene. None of the isomeric Z alkene formed Bro, I am getting lost in this stuff. What stereochemistry do you expect for the alkene obtained by E2 elimination of 1R, 2R? So this is S. And that is S. Wait, is it S? Wait. I think that you go This one wins, then carbon, carbon. But then here, this is priority 2. So if you look like that from above, it's clockwise. So you gotta flip it, it's S. Now we're going BR to here to there. Yeah, that looks like S as well. Oh yeah, this, okay. One R, 2R, 1,2 dibromo, 1,2 diphenyl ethane. How did they draw it? I need to learn to draw it like this. H C B R. Wait, no, the H needs to be up here. Then this needs to be BR. Now I need to erase this to figure out what the hell is going on. If you look from above, you're gonna go, and this is BR. Then you're gonna go 1, 2. That's an R. If you look from above, you're gonna go. Wait, no, but that's an. Yeah, so that's an S. If you look from above here, you're gonna go S, and it switches to R. So this is the phenol. Okay. So I believe that this is the R. R. Okay, now what is the question? What stereochemistry do you expect for the alkene obtained? Draw Newman. Okay, so first off, let's draw the Newman projection. but what stereochemistry do we expect? I don't know. It's an alkene. It should just be no stereochemistry. What? Wait, here we get the E. Because this goes like this. Yeah. Did I do this wrong? Because I then got that we should get. Why is it Z? Wait. No, what? Yeah. This one, what? What? Why is it? Wait, but this one, it said it was Z. Base H anti to a leaving group B on the adjacent carbon. So Newman projection, yes. I did that. Build a Newman projection for 1R, 2R. Oh, bro, I'm actually. Wait, no. What? What do we end up with? We end up with. Here is Z. But it is E. Okay, that's freaking weird. That is freaking weird, bro. The E2 reaction in cyclohexane. Wait, okay, should we try to do this one? I probably need the practice because I don't know what is going on right now. What stereochemistry do you expect for the tri-substituted alkene? Obtained by E2 elimination of the following alkyl halide on treatment with KOH. I bet the answer in the textbook is just like E. Yeah. It's like 3-methyl-2-pentene. So first off, the molecule is 2-bromo, 3-methyl pentane. it's this one. And I guess you could rotate this one too. BRs on C2 beta carbons are C1 and C3. Remove H from C3. But like, this one needs to come around, right? And then it. Okay, so this one's coming out at us, and this one's going back. This one's coming out at us too. Yeah, this one's coming out down here, kind of like this. This one's going out back there. Or we're rotating it clockwise. So this one goes to here, this one goes to here, and this one goes to there. Then we fling this around, we drop this off. This has the double. Now the highest prio group is going to be this. So this went back here, didn't it? This is going to be planar now. So I'm going to guess it's Z. Is it Z? Whatever. Shit's dumb, man. Or transdiaxial. Yeah. If either the leaving group or the hydrogen is equatorial, the elimination can occur. Yeah, but so what? They're gonna flip, aren't they? Don't they flip? Alright.